I'm glad that you're here. In the 20th century, we architects worked really hard to enable you to ignore us and just get faster computers. Going forward, that's not going to happen. And so if you want to do and have more capable systems, at least some of you are going to have to work crossing many boundaries. And so it's good to look into that, because this is a good chance for you guys early in your career to step out in a way that some of your senior colleagues are not going to do, right? Once they've spent 20 years ignoring other layers of the computing stack, they're not going to suddenly stop. Okay, so what we're going to do is a little bit of a background on the big picture. And the other thing that this talk will do is that it'll show you the process that CCC uses. So even if you don't care about architecture, you can learn a little bit about the process. I have a couple slides on a very exciting new area, quantum computing, where we just ran a workshop, and then Tom will give some of the IEEE rebooting computing talk. He tells me whole talk in one slide, right?
Yeah, about 8.
More or less. Okay, so what CCC is 20 people, and at 20 people in a room, only one person talks. That doesn't work well for academics who are used to doing at least 75% of the talking in the room. So we organize things into these task forces. And this year, I was the co-chair with Kathy Yellick, who has rotated off. She's a great computational scientist from the University of California, Berkeley, and Tom was an external member. Among our accomplishments recently is the Architecture 2030 report, which is about a year old now, which I will tell you about it. And then this year we've done a couple of workshops. One is on digital computing beyond Moore's Law, which I'm not really going to talk about because the slides are not ready. Another one was next steps in quantum computing, computer science's role, and this one I will have a few slides on. The third one is upcoming in January in Hawaii, if you're interested. It's on thermodynamic computing, so we had to go somewhere warm. And this is an example of one of the sort of new ways to compute. And we feel like going forward, the conventional way should be pushed as far as possible, but it's time to explore some new ways. And in a lot of ways, this is very exciting, because when the conventional method was improving by a factor of 2 every 2 years, it drove out anything else more radical. Okay, so this 2030 report was something that I was involved with, and this came out about a year ago. It followed on a study that I had led 5 or 6 years before. And this slide used to have overlays, but let's just do the non-overlay version. So on the left, we have in the 20th century, like we computer architects, we just did computers. We didn't pay attention to where the computer was. We tried to make the performance completely invisible to you, and the technologies that we built things out of were like, they got quantitatively better twice as fast all the time, but they were really changing in very predictable ways. Going forward this century, we're going to have to really pay attention to where we put the computer. What you're going to put in a wearable is way different than what you put in cloud computing. And because we're not getting the single-threaded performance, we have to pay attention to parallelism, specialization, and this cross-layer that I mentioned. And there's all kinds of new technologies, and there's all kinds of cross-cutting. And that was a study that we did in 2012, and that, by the way, resulted in $16 million a year of funding from the National Science Foundation that I believe is still ongoing. So you can really have impact. And if you run a study too well, you can end up being CCC chair. And so what these guys were asking a year ago was sort of what's changed. And one of the key changes is that machine learning was even then emerging as a key workload, and now it's everywhere. Specialization is a kind of an interesting word. We used to build general-purpose computers. But what happens when you have something like image processing, which is special, but billions of people need it? So we have these new opportunities. The cloud is really important, and this Moore's Law, which is, strictly speaking, the number of transistors doubling every 2 years, but it was viewed by the general public as performance doubling every 2 years is really ending. Everybody but Intel says that. Intel says it's not ending, but they've just delayed their latest processor again for maybe the 5th time. So the workshop covered many things, and in this little 10-minute introduction at the end of the afternoon, I'm not going to cover everything that it covered. I'm going to talk a little bit about this specialization gap and how there might be some interest in what we're called democratizing hardware design, and I'll define that. Okay? And so this really is the fact that if we're not going to get generally faster transistors, what we have to do is we have to target things more specifically to specific tasks. So sort of instead of doing everything pretty well, we're going to do a narrow thing really well, and another thing narrow thing really well, and another thing narrow really well, and that's going to be sort of a new kind of computer. But there's all kinds of challenges. How do you design a specialized thing with reasonable effort? And more importantly, how you program it. We architects can sometimes be guilty of doing unbelievably convoluted hardware and showing on some little deep program like matrix multiply that it works well and say, hey, no, you go do your full application, and that's not going to cut it. The other thing that really came out of this is that sometimes the way to really get change is to not just focus on your end, but focus on your means. So what about doing open source hardware? That sounds like an oxymoron, but let's think about that for a second. So first of all, is open source software good for anything? Well, if you go back a decade or more, Bill Gates acted like open source software was like an assault on capitalism as we know it. But what it's done is that very rational capitalist enterprises contribute to open source software. And it's really changed the startup scene and the innovation scene tremendously, right? Because if you want to do a startup, you can download all this generic stuff and then add your special sauce. And you can get to the point of learning whether your special sauce is working with much less funding and much less time, and you can iterate, so-called lean business models. Well, right now, if we're going to have to do hardware, software design together, unfortunately, the hardware is a complete laggard, right? If you want to do something boring like a memory controller, which you got to have if you're going to have memory, but it's not your special sauce, it's a really big hassle to license this. And so we think there's a real potential in sort of unleashing innovation like what happened in the open source industry for hardware. Now, there's many specific challenges, like you actually eventually have to make the hardware. And I also think this is going to, if it happens, it's going to happen first on sort of lower performance things, right? You're doing a wearable, you need a little processor to do something. You don't need the latest and greatest processor. And so look what happens over the next 5 to 10 years to see if this happens. Somewhat contemporaneously with this, by the way, DARPA has a big push on this part of their $150 million electronics resurgence initiative called POSH, which has open source hardware. So who knew even the military wanted open source hardware? Okay, so I don't know how I'm doing on time, but so the next thing I want to talk about is this quantum computing workshop. So the idea here was that there's a lot of people doing theory in quantum computing, and there's people doing the physics, but as we know, computer systems require things in the middle, right? If you can imagine people doing, in the 1950s, doing math and other people doing hardware, transistor tubes, radio tubes, but what about everything in the middle? It took a while to understand what's in the middle. So this workshop was about trying to figure out what happens in the middle. One of the things we recognize is that right now, quantum computing is really exciting. And it's following a classic business thing called the Gartner hype cycle, which if you don't know about, let me explain, because it's valuable well beyond quantum computing. So on the y-axis is like how exciting and hype something is, and on the x-axis is time. And many technologies get hyped, and you got this gigantic hump at the beginning. And then they go down into what's called a trough of despair, when they didn't actually completely change the world in 3 years as promised. And then they either die or they climb back or they eventually change the world. Okay, so quantum computing is pretty high on the hype cycle right now. And people are going to soon discover that real applications are not coming in 2020. So we have to be a little bit more measured about that. The other thing is, this comes back to the abstractions. Abstractions are important for going behind toy problems. So this is a very useful thing that's done in computing all the time. Anybody want to guess what it is? It's 8-bit A plus B, okay? But if you always have to specify it this way, it's going to be a lot harder to specify something more complicated. So abstractions are important. Well, a problem with quantum computing right now is if you want to program a quantum computer, you got to specify it in a way that's worse than this, because you have to pay attention to the properties of the gates. And we say, that's really going to limit how useful this is. And what the right abstractions are, we don't know. Okay, and the other part of the roadmap, and this gets a little technical, so I'll mostly skip it, is that there's issues with the number of gates and the error probability and things like that. And there's a belief that, one of the things that Moore's law was, it was not a law of nature, it was sort of business law, which sort of got people on the same page. So that in 2 years, when transistors were going to double, the equipment manufacturers were going to be able to build the machines that you could fabricate those transistors. The architects designed processors that were going to use those transistors. The software people bloated their software enough to use those transistors, and everyone went on the same cadence. So the idea is, can we develop a cadence for quantum computing so that people can be on the same page? And we're just at the start of that. And so I believe that concludes my remarks. And now I'll turn it over to Tom.
Thank you, Mark. All right, so Mark touched upon a lot of the themes I'm going to talk about, but let me see if I can tell you why you should care, okay? So there's too many Moore's laws. There's the Washington Post, New York Times, CNN law, which goes, golly, computers keep on getting faster, right? That's what the general public knows. I call that Moore with one O's law, or I want more Moore's law. Now, here's what Gordon Moore actually said. He said, transistors get exponentially cheaper over time. So he originally said, if you pay me $1, I'll give you so many transistors. If you wait a year, I'll give you twice as many. And then he revised it in about a decade later in 1975 and said, actually, it's if you wait 2 years. And so most people average those and say it's 18 months, but that was completely bad math. In any regard, that's what Moore's law is. It has nothing to do with performance. So you could say that that's fake news. So I fought this war when we were starting Rebooting Computing back in late 2012, and I fought it for a while, and I've lost. So I've just decided that we have to address both interpretations of Moore's law. No collusion, but okay. So here is an example of what architects have been doing to keep that Moore with a single O going. In 1995, just about then, what happened was the wires on chips got so long that we couldn't clock them fast enough. Electricity actually takes time to go down a wire. So what ultimately we had to do was hide a lot of that from you and continue on with the single O Moore's law up here. While the real Moore's law, if we just followed transistors getting smaller, was not making computers nearly as fast. So that was a fun gig, and we did that for a decade. And then we hit this chip. And people ask me, when did single-thread performance scaling stop? That's easy, first quarter 2005. How do you know it that precisely? Because that's when the Intel Pentium 4 Prescott was released. And at its design frequency, it dissipated 200 watts per square centimeter. Okay, I realize most of you are number numb, and 200 watts per square centimeter is, okay, kind of hot. That's the same density as an operating nuclear reactor core. Okay, so we don't want Chernobyl in your laptop, right? So what do you do if Mr. Moore, with 2 O's, keeps on bringing you more transistors, but you can't clock them any faster? This is the plot of clock frequency over time. And you can see right about 2005, we went oops, and we've leveled off. What you do is you clock multiple cores more conservatively. And it's not a great solution because multi-core, although it sounds great, you have to reprogram to really use it. And how many people here have written a parallel program? Anybody? How many got it to work the first time? Yeah. It's hard. You did? Wow, that's impressive. Yeah, go for it. Quicksort? I don't know. Hey. So in late 2012, Ellie Track and I realized this. We went to IEEE Volunteer Brass and we proposed something called an IEEE initiative. And we started this thing called Rebooting Computing. The name, the name was originally, let's do something to do post-apocalyptic computing or whatever. I couldn't come up with a good name. One morning in the shower, I said to my wife, I got it. And she said, what? I said, Rebooting Computing. And she said, that's the most ridiculous thing I've ever heard. And I said it to Ellie, and he liked it, so it stuck. Turns out that Peter Denning had used this about 5 years earlier for a different effort, and so we had to go to Peter and say, is it all right if we reuse it in IEEE? And he graciously allowed us to. But here's what we decided. We held 4 summits. We had thought leaders and important people. A lot of times these are people who we would knock on their door or knock on the side of their cube, and they would go, well, why are you talking to me? Everybody thinks I'm crazy. You know, that's who we want. We want you. We want crazy people. And we bring them out and we talk about different ways we could restart performance scaling. And we realized there was really 4 levels. There's the more, there's hidden changes, architectural changes, which disrupt some of the software stack, and crazy stuff. So let me just go through them real quick. More, that sounds like a good idea. This is something engineers love. This is an energy delay product. So energy and delay are here. This plots different transistors if you build a 32-bit adder. This is due to Dmitry Nikonov and Ian Young, who's a senior fellow at Intel. And this shows you what the different proposed transistors we have can do. This is our load line. Those green dots are what we have today. And you'll notice something. There isn't a heck of a lot below that load line. Where we really want to be is in the lower left corner, but there's not a golden bullet. Some of that makes sense. When we get to 1.5 nanometer, that will be 6 silicon atoms wide. So as we go down, we're getting to the point where we're actually accidentally making quantum computers. Let's talk about hidden changes. This is one of my favorite examples of hidden changes. This is a project that was funded by IARPA. It has several performers. One of them is Northrop Grumman, and they've had success building a cryogenic, Josephson junction-based, superconducting processor. In this case, it runs the MIPS instruction set, and eventually you could use that in a data center. Now, this used to be crazy because people would say, no, so what? It might be faster, but you have to pay that whole cost of cooling it down. Well, I think this is an indictment about just how bad CMOS has gotten, because the cost for equal performance of cooling that is 1/100th the power. The cost of the compute plus the cost of cooling it is 1/100th the power of just the CMOS solution. So if you think about that, CMOS is really bad. But again, nuclear reactors, we got into a bad place. Let's talk about architectural changes, because this will probably impact your lives the most. Mark mentioned one that is very dominant, which is this idea of using special purpose accelerators. And this has been around a long time. If you go back to really what I consider the dawn of computer architecture, which was machined by IBM called the IBM Project Stretch. It had an attached processor just for cryptography. You can see who helped fund this for IBM. Anyway, another example is GPUs that have worked here. People did not mind reprogramming to take advantage of GPUs because what you got was really cheap parallelism on your desktop. So you're going to have to reprogram to use this. Another one that is very active is this idea of approximate computing, which is to trade off accuracy for energy efficiency. The problem with this is that if you look at a plot of a lot of times this begins or ends with human perception. So because we're good at dealing with, well, pretty bad images, we can manage this. But you go from looks good, looks pretty good, looks great, look, yeah, maybe, boom, it's horrible. And it's finding that limit where you can trade off approximation for energy efficiency without falling off that cliff that is difficult. All right, let's just talk about our favorite non-von Neumann approach, which is quantum. So let me tell you some things you might not know. There are two flavors of quantum today. One is called quantum annealing, which if you know the simulated annealing algorithm, it's similar to that. Some people claim that's not real quantum. Whatever, okay? I'm not gonna fight that fight. But the convergence time it solves optimal problems with a near optimal solution. The convergence time that you have to wait for the answer is a function of the noise floor. So the more expensive a problem is, the longer you have to wait, and the certainty in knowing when you have the answer gets harder. Then there's the one that you read about a lot in the popular press, which is gate-level quantum. There are two known algorithms. You might read a lot about quantum, but all we know really right now is we can do two things with it. We can do Grover's algorithm, which is a version of search, and Shor's algorithm, which is, well, the death of cryptography, if you will. Shor's algorithm is factoring. The leading devices that you build these out of, the qubits, we have right now two leading devices. Transmons, those are superconducting. So instead of where that prior thing I showed you that was balmy, that was 4 degrees, sorry, physicists will kill me. That was 4 Kelvin. Okay. This is working at millikelvin. So this is much more expensive to get to this level. The coherence time before these things lose their quantum state is in the order of 10 to 100 milliseconds. We need several orders of magnitude to put together a real thing. Microseconds? Yeah, micro. Did I say milli? Micro.
It's a factor of 1,000.
Yeah. We want to get to milli. We're at micro. These are noisy, and you actually have to actively do error correction. And you put those two together, and it means in order to get something that functions like the qubit we want, we have to use about 1,000 physical qubits. So when you hear Google say, we have a 175 qubit chip, they're talking about physical qubits. We're a long way away from where we need to actually have one functioning qubit that could start to array. That being said, there's a new field in, hey, can we use crappy qubits to do something interesting? One interesting thing we can do, it's kind of ironic, is to do quantum chemistry. And we can model new substances using quantum. And that is neither Grover's nor Shor's algorithm, and it may well be the first thing that quantum succeeds at. The last piece that's kind of ouch is you look at this and Intel or something, they'll hold up this chip, right? And they go, wow, this is the chip. What they don't tell you is what's in the back room. And for each qubit, you need waveform generators, interfacing, and measurement instrumentation that consume kilowatts. So, in fact, they consume so much that the cooling to get to millikelvin is just a tiny fraction of the power. We had this company that moved into our little research park at Georgia Tech, which is Keysight, which is the old HP, became Agilent, the old instrumentation piece of HP. They love quantum because they're selling instruments left and right. Okay, here's the main thing though, and this is the fun time to be in the field of computing because all the layers of abstraction that we're so comfortable with are coming crashing down. I have a friend who, when I started talking about this a few years ago, he said, Tom, all this crazy stuff you're talking about, I have a solution, I'm gonna retire. That is one approach, okay? But if you have a crazy idea, bring it. The epic of risk-averse hardware is long over. And if you wanna learn more, here's some URLs you can look at, okay? You can go to the almost unimaginably long rebootingcomputing.ieee.org, or the new semiconductor roadmap, which is now hosted by IEEE called IRDS, or this is a conference we have coming up, if you want to see more about that. Done. Let's take some questions.
Okay, so come to the mic, state your name and affiliation.
Software people need to catch up with the hardware folks in terms of even stuff like non-uniform memory access and stuff like that. Do you think it's that the hardware folks need to be more imaginative, as you're saying, or is it like a little of both?
Well, so first of all, in many software situations, perhaps the performance is good enough and you're doing some other kind of innovation. However, if you want to go further, yeah, we got to talk. And I think it's bad to blame either side. I mean, we architects tried really hard to avoid talking to you and allowing you to not talk to us, but those times are gone. And so, as researchers, if you, like make your students take an architecture class or have them write some parallel programs, it's an additional edge you'll have in your field. I mean, Google, for example, is pushing very hard to do these hardware accelerators. Why? Do they love hardware accelerators? No, they want to do a lot of machine learning, and they were fearing I can't remember who did it. It's called a success disaster. They calculated that if everybody used the Google equivalent of Siri for a couple minutes a day, they would have to double their data center capacity, and they thought building hardware accelerators was easier.
Let me just
Go ahead.
Follow into what Mark said. I've been asked this a lot. Software engineering in a lot of ways still hasn't even embraced parallelism. I think I've given this talk in front of software engineers, and it almost brings them to tears. I think if you, in your schools and your departments, have software engineering faculty, go give them a hug. It's going to get really worse. We have to talk. We built this high-rise building with these nice cushy levels of abstraction over the last 40, 50 years, and we're going to have to go between the floors. And this has got to be an all hands on deck thing. It's a real inflection point. This is a fundamental shift. And for better or worse, it's happening in your lifetime.
I'm Katie Schumann. I'm from Oak Ridge National Lab. I'm the lunatic fringe, as Tom likes to say. I'm a neuromorphic computing researcher. So my question for you kind of leads off on that, which is, right now, I would say both neuromorphic and quantum, the levels of programming abstraction, we're like at the analog of the binary or maybe assembly level in some cases, but basically we're programming at the binary level. So I often give the talk, and I've heard Tom give this talk multiple times as well, that we need the software engineering community to buy in. I think we also need the algorithms communities to buy in. How can we do that? Do you have any advice for how to continue to get the buy-in from those communities? Because we need their help if we're actually going to be able to use them effectively.
Yeah, and I think that they're starting to realize there's something up. I used to say that, hey, my relatives would come to me and be mad that they bought a new laptop and it wasn't any faster, right? But I think people have gotten so inured to the idea that computers aren't getting faster, now they just complain that their keyboard broke. So we do have to get to the point where everybody understands this is an all-hands-on emergency. And so that's why I'm happy that a lot of you who are not in the hardware area are in this room, and hopefully Mark and I are scaring you. And remember, I'm sorry, one other thing that I said, that the action is really at the fringes. So it's really important to be cross-disciplinary in this age. Go ahead.
Yeah, I was going to say, and it's not that everybody is going to cross over, it's going to be the pioneers. One of the great things about the research system in the United States, especially in universities, is that, you know, assistant professors don't work for associate professors who work for full professors, which makes for a very conservative organization such as you have in Germany. Here, you guys are trying to set out, make a name for yourself, make a different name. Let's say you just got past tenure. I mean, this is a time when you can put into your research portfolio that Greg Morissette was talking about, a couple more radical things, and see if you can, you know, with a student, reach down and do some other things and be the pioneer, right? Either, you know, be the person that writes that early paper that doesn't get it completely right, and thousands of people have to cite it as they improve it.
So I don't think it's just the software engineers who are going to need a hub. So I love cross-disciplinary research, and you know, as Mark said, the XPS is now SPX because they can't keep the letters in the same order. Great opportunity for pursuing that. But recruiting students to perform cross-disciplinary research is, I think, a strictly more difficult task, and perhaps the same way that parallel programming is a strictly more difficult task than serial programming. Because all these abstractions were built to improve productivity, and there's a grandfathering issue. You have a bunch of students trained in abstractions that made them very productive in ways that are no longer relevant, and we have to sort of rehammer them into cross-layer people.
That's a very good point. This is how I've structured my group, in that I have students from different levels of the hierarchy, and that's one way to approach it. I'm joint appointed in ECE and NCS, and so I have some ECE students who, I have one who started out in analog design. You got to do that kind of thing in your research group. You can attract those students to work with you if you're wide-eyed crazy and they feel the energy of that. And in general, I think that it is difficult right now. It's difficult for faculty as well. Assembling vertical teams of expertise should be something that academia does well, but we do it incredibly poorly. And so we're trying to get better at that. My strongest recommendation is that every time you're in front of students, you let them know that this is a problem, and that the future, everyone needs to worry about it. Until things settle back down and we find new layers of abstraction, and we will eventually. But until that happens, now's the time to work on cross-disciplinary. Maybe learn Ohm's law. You know, I have a lot of thing that cracks me up the most is students who will come to me and say, you know, I went into computer engineering because I didn't want to sit in front of a terminal all day. Then we teach them Verilog, and they realize they have made an error.
Right. They get to program in a lousy programming language instead of a cool programming language.
It's inherently parallel.
Oh, yeah. So I guess my experience is that students aren't as rigid as you said. They're much more experimental. I see much more rigidity in the senior faculty. So somebody has been in programming languages forever and didn't have to learn other things. They don't necessarily want to go here. But that's where you get, you know, generational shifts. I guess I disagree a little bit with Tom. I don't think it's an all hands on deck. It's a key innovators on deck, and then what we have to do is shield a lot of people from this. These machine learning accelerators, for example, are flourishing in part because TensorFlow and the other equivalent high-level APIs give people a way to access and express what they want in their computation in a way that's convenient for them and still has enough structure there that the lower level of the software and hardware can exploit it. And I think that's a example of a success.
I don't think we're quite there, because a lot of times we're hand converting Python code that they wrote, but we're getting closer.
Aruna Balasubramanian from Stony Brook. I'm actually going to beat the dead horse a little bit more, in the sense that, so I also do applications and more systems work. And one of the things that I found was hard, and this was a long time ago, 3 years ago, I do mobile systems work, and I found that there was something called a sensor hub chip that's on most of our phones. It does like extremely energy efficient sensing, but it didn't actually provide any abstractions to the higher layers, except Apple. And so the way that you need to use this, if you use any other mobile that's not Apple, is that you have to download their library and then write the specific kind of code, which is never going to work because it's not going to work for all your apps. An app developer is not going to do that. So I wanted to ask about what you think about these vertical integrations from the company's point of view. So Apple, for example, builds their hardware and software, and they are able to work towards, making sure that they all work well together. Whereas the companies are not the same, like Intel or ARM provides a chip, Google does the software, and then there's this disconnect, and you don't really know how to have a uniformity to be able to do some of the things that the hardware provides in software.
Right, so I'm senior enough to have watched this wheel turn more than once. So when I started, there were big vertically integrated companies like IBM and Digital Equipment Corporation that did everything from applications to building the chips in the computers. And then in the PC era, we got this much horizontal stratification. There's Applied Materials, Intel, Microsoft, Adobe, Dell and Adobe, right? And so you're exactly right. What's happening is that there's a lot of vertical integration on. So I'm currently on sabbatical at Google, which is a company that sort of only does cloud stuff, but now they are actually having design teams design chips. Facebook wants to design chips, Microsoft is designing chips, and hardware companies are trying to go up and get into the software space. NVIDIA has been reasonably successful, and people have asked me, is it easier to be a software company and go down to hardware or the other way around? And I don't think there's a clear answer, and it's probably particular to the corporate culture and leadership.
Fair enough. I'm surprised you didn't say anything about Apple being from Wisconsin, but that's fine.
Apple does fine products.
They do fine infringing products. Yes, they do.
That's a different story, but yeah. So it was interesting. I previously consulted for AMD, and we had some ideas for accelerators, and trying to convince Microsoft to support them in their operating system was very difficult because I don't want to pick on Microsoft. I mean, they were being completely locally rational, right? They were saying, well, what is the value proposition for us? And a vertically integrated company can look at the value proposition across the whole vertical. That's the good news. The bad news is they tend to be a monopoly with each other, right? And that leads to inefficiencies. And in the PC era, it was better to have interchangeable parts competing than it was to have the high bandwidth creative connections. Okay, other questions?
What was the parallel program you wrote that worked?
Oh, it was a no shared data program, so it was easy.
Oh, embarrassingly parallel.
Yeah,
I'm sorry, abundantly parallel. Abundantly, not embarrassing, I'm told. It's abundant.
I do have another thing, though. I know that one community of software people who do care a lot about the specifics of the hardware that they're programming on is the game development community. So people writing software for like PlayStation 3, PlayStation 4, where there's a lot of kind of bespoke architectures, or for even mobile phones where energy consumption can be extremely important. Are there folks from those communities that are already involved in this kind of initiative? Like, are there guidelines that, or practices that you think might be shared in terms of like programming maybe cache oblivious algorithms, or working in terms of like programming sort of from the top down with this, with the hardware that you're programming for in mind? Are there sets of guidelines that we can use to maybe transfer out of like into other points of programming practice?
Yeah, it's an interesting question. What I've seen instead is a community grow up that is interested in what's called performance portability. That is the idea that I write an application for one architecture and I can take it to a different architecture and somehow it's still really good. It's turned out to be a really tough problem outside of just saying GPUs and CPUs. But I think we're going to get to a level where that gets, what we're going to do is an API level programming. And API level programming works and it doesn't work because then there has to be someone who writes the individual API functions and specializes to the hardware. And that in and of itself is just like you said, in the gaming community or in the embedded space, you're down there optimizing by hand to get the last cycle or the last joule.
So I haven't seen the gaming community reach out and try to promulgate their methods. I think they seem to be pretty competitive and not wanting to share. Another community that really pays attention to performance is the high performance computing community. And they've been doing parallelism for a long time. And about 10 years ago, I was trying to rally them to, like, why don't you teach the rest of the community what you know about parallelism? And it never happened.
Yeah, even at that level, we have a problem in computer science education in the sense that we bring students in and we teach them programming as sequential programming. We teach them Q-sort, which is inherently parallel as a sequential algorithm. And in some ways, there's been studies that show, that humans are okay thinking in parallel. So we're actually hammering it out of them when they bring them in, when we bring them in to teach them computing. I've seen some places experiment with parallelism first in the curriculum. We just have to see quite a bit more of that. And also, I think algorithms first is another important thing because as an architect, I used to shun algorithms. Now I have to swim in that space. And I think that for someone to be well-rounded, they have to understand parallelism, algorithms, energy, and power these days.
Okay, other questions, or do you want 15 or 20 minutes of your life back?
Oh, come on. How many people knew Moore's Law was ending? You're wrong.
Wow.
Well, that was fun, right? You're thinking of Moore with one O. But the roadmap says we'll continue to make transistors smaller. It's slowing down, but we'll continue for about another decade. What comes next after planar transistors, when we've already started to do this with FinFETs, is you build 3D transistors. And then we'll be doing monolithic 3D. What we do now when we do 3D chips is you build a chip, you build another chip, you thin the back layers and you slap them together. But this will be single silicon at manufacturing time with multiple layers of logic and memory together. That's necessarily going to change the programming model in addition to that, because now we're going to have no more caches. We're going to have local pockets of memory, and you're going to have to manage both memory and computation like the good old days. Yeah, no, come on.
So that's kind of the situation with GPU programming, right?
Yes.
You've got the local storage and the local memory, and the host memory, whatever. Do you think that all the programming, or at least big chunks of the computation that we do, are going to, on the programming language side, need to be restructured to sort of try to separate out that the more memory movement aware parts from non-memory movement aware parts?
I think it might. So the thing that we learned with GPUs and then CUDA and Open CUDA Lite, as it's true, is that you have to change your algorithms. You have to focus on the hardware. So you have to cut through the layers. And the pull there, like I said earlier, was that it was really cheap parallelism. So that was the pull. Now there's going to be a push that we don't have any choice. But, that being said, there's also a challenge to systems people in how much of that can we hide and make it easier for programmers.
I mean, the way I would look at it is that, you know, the simplest model of memory is that there's just a flat array, and that's a start. You're not going to get high performance thinking about memory that way. Now, on the other hand, if what you have to think about is you have to reason about the detailed crapola of this hardware, I mean, that's okay if you're doing a driver for the iPhone X and that's what your job is. But in between, what is the right level of abstraction? And I like the word model, right? Models, George Box, a great statistician, said all models are wrong, some are useful, right? So is there a model that, you know, in a given situation gives you enough that you get the first order optimizations and doesn't swamp you with the others? And I think exactly what the model will be for some of these 3D architectures is to be determined. By you, maybe. Okay?
So, to borrow a term from the DOE lingo, we started talking about extreme heterogeneity in our system. So a lot of what we've talked about today has been kind of like, what are the future architectures? So we're going to write a program that runs on this system. When do we start to introduce to the software community and the algorithms community, okay, now you have a bunch of these systems, a bunch of different, very, very different, GPU, but also FPGA, but also Approximate, but also thermodynamic, and also neuromorphic, and also quantum, and you're going to write a program that is going to optimally try to utilize all of them. When do we bring that idea in?
Well, I'm currently on sabbatical at Google in the group that does consumer electronics, and we've already brought that in, right? You know, and Apple has already brought that in, and so it's as William Gibson said, the future is here. It's just unevenly distributed. And so that's happened in the embedded space where people can be very specialized. It's not happened more generally, and when it's going to happen, I don't know. I mean, homogeneous parallelism has taken a long time to spread, so this extreme heterogeneity is, amping it up another level.
But I agree with everything Mark said. Let me just put another twist on it in that another way to think about what we've been trying to do for 50 years is hold up this illusion of general purpose computing. There really is no such thing. It's really been that if you want the fastest, the best performance, you have to go to special purpose hardware. It's just now it's become more of a market or a bazaar. And programmers will understand that I think they'll understand that as time goes on, that I'm not going to write in a general purpose programming language for a general purpose processor. I'm going to write in a domain specific language for the problem I'm trying to solve for a particular domain specific accelerator.
And let me give an example of that, which I just got increased familiarity with. I was talking to somebody about Halide. So Halide is a language that it was, Stanford and MIT, and it's being used in a number of places, including Google, for image processing. And it breaks your image processing down into two pieces. One is you describe like what you want to do for each pixel as a filter, and then there's a series of filters. And the language infrastructure just takes care of iterating across all the pixels and creating halo rows, and so that when you tile things. And then completely separate from this functional language, you specify a schedule, like how you want to order the computation so that there's good reuse in the memory hierarchy. And one of the things that's cool about it is that a bad schedule doesn't change the function of the program, it just changed the performance, so you can optimize it a lot better. And you can explore schedules more quickly because you don't keep breaking the program. Imagine even doing a matrix multiply. If you change the tiling, you can break the program. And so I think that's an example of something that is really good for what it does, and people are going to probably have to learn that to program accelerators. And some people will be protected from that because they'll be above that and they'll be using libraries, which in turn have been using Halide. But in the foreseeable future, I don't think we're going to have a general purpose language that's going to just automatically compile to this extreme heterogeneity. And maybe someday, but we'll have to do special purpose first.
Yeah, I'd go further and claim boldly that will never converge, because to use these accelerators, you have to do things at the algorithmic level. And so it's really hard to have a programming language that is devoid from the algorithm or abstracts over the algorithm. So I think we will end up in a situation where instead of teaching students, Java, et cetera. We will be, or Python now has become very popular. We'll be teaching them several different domain-specific languages that are important for getting different tasks done.
We'll teach them how to learn domain-specific languages quickly. Okay?
Oh, you got another one? Yeah.
I'm actually going to push back on against you, Tom, on whether or not 3Ds make anything better.
Whether or not...
Monolithic 3D, and so the end of more or not.
Okay.
So end of more in terms of whether or not there's going to be more integration, I agree, integration is going to continue. So that aspect. But from the, ultimately why, because Moore's Law wasn't a law, right? Moore's Law was a self-fulfilling prophecy driven by a value proposition, right? That you were going to be able to actually get dollar value on the y-axis value out of doing this new thing with more transistors.
It was an economic observation.
Right, exactly.
Yeah.
And so, in that vein, what I see as the practical end of Moore is the end of the value proposition in terms of diminishing markets of people that will be able to extract value from greater integration. Right. So for instance, we can get more transistors, and we go 3D, and we get memory scaling. And,
I get your point.
And for the parallel GPU type algorithms, it's beautiful, but GCC is still running at whatever speed it was before. Then we're losing little bits of the market. We're getting a polyfurcation of the people who are able to get value from these additional pieces. And so in that vein, I think it's still worthwhile to talk about the end of Moore, and perhaps not the end of, because we're arguing about derivatives, right? It's like the first derivative got smaller, it's still positive, but we should run around as if it's slightly the end of the world.
I agree, I violently agree with everything you said. So I used to say, Moore's Law is ending, but Intel came out very strong against that. And he's now retired, but there was a New York Times reporter, John Markoff, who asked me, we were just chatting on the phone. I forgot to say it was off record. And he said, what do you think about Intel saying Moore's Law is going to continue forever? And I said, well, if that's your entire business, what do you think you're going to say? And that showed up in print with a lot of people at Intel, no longer my friend.
But it's a true statement.
It is a very true statement, but not one that they want to face, right? So in a very real way, Intel has put two faces on. They advertise more with one O, but what they deliver is more with two O's. And I agree that the utility and functionality you're going to be able to get out of 3D is going to be more and more challenging. But I also realize that there are cost savings for doing an entire system at that level. And it's already coming online. So it will happen. It's just a question of what do we figure out? How do we figure out how to get value out of that? It's going to be more challenging. So I agree with you, like I said. If you do more with 1.0, then yeah. That ended actually technically in 2005. People, it's actually not Moore's Law we were talking about, it was Dennard's scaling. And people got those two ideas confused. Good for you, good. I do too, but.
Architects too, but. Yeah. All right, last questions? All right.
We'll be at the poster session if you want to bug us some more.
Yep. We'll declare success ahead of schedule. Transistors are getting a little faster. Okay, thanks.